So today's lab experiment is about capacitors. And capacitors are circuit elements. You put them into electrical circuits, and they basically consist of two conducting sheets with an insulating space between them. So what does that enable you to do? So when you put a voltage or a potential difference across the capacitor, what happens is you have current moving, at least initially. And so the current gets to, or the electrons move to one of the conducting sheets of the capacitor, but because there's an insulating space between them, they can't jump across. So a buildup of charge happens. So you get a buildup, you get a charge negative Q on the side that's facing the negative, where the negative potential difference is. Now they can't; those extra electrons can't jump across the insulating gap, but they can repel the electrons on the other side, and so those electrons get booted. And what happens is you have a charge positive Q building up on the opposite face of the capacitor, and the charge builds up until the potential difference across the capacitor equals the potential difference feeding in. And so you have a potential difference delta V. And the ratio Q over delta V, so the charge that builds up to the potential difference across it, is constant, and it equals the capacitance of the capacitor. So a higher capacitance means you can store more charge for the same voltage. And so you'll be able to see that in this particular experiment. Now you can connect multiple capacitors in combination. So the first type of combination is series. And in a series circuit, or in a series segment of a circuit, you have one capacitor and then you have the other capacitor. So they're connected to each other. And so the back of one is connected to the front of the other. And so what happens is the electrons go to the first one and then can't go across the insulating gap, and so they repel the electrons out. Those extra electrons then go to the second capacitor, so they get the same charge Q building up on them and being stored by the capacitor. So each capacitor in a series circuit, or in a series segment within a circuit, gets the same charge Q. And the charge builds up until the individual voltages across the capacitors add up to the total voltage feeding into that segment of the circuit. And so the total capacitance obeys, in a series circuit, obeys what's called an inverse sum relationship. So 1 over C total is equal to 1 over C1 plus 1 over C2, and then so on if there's more than 2. The total capacitance is actually less than either of the individual capacitances, or any of the individual capacitances if you're talking about multiple circuits. When you connect the capacitors in parallel, some of the current goes to one capacitor and some of the current goes to the other capacitor, so they branch off. And so they don't get the same charge in both. What happens is the voltage across each is equal to the voltage that feeds in to that segment of the circuit. The charges add up so that the total charge coming into the parallel segment is equal to the sum of the charges that build up on each capacitor. And in a parallel segment, the total capacitance is equal to the sum of the individual capacitances. So C total is equal to C1 plus C2, and if there are more capacitors, plus C3 plus C4. In this experiment, we're only going to be looking at 2 capacitors. So the first thing you're going to be doing, and that's the first of our 5 video clips, is measuring the capacitances using the digital multimeter. And so you'll see they have nominal values of 100 microfarads and 200 microfarads, but the more precise values you get with the DMM are a little bit different than that. Not a whole lot, but a little bit. So you're going to be working with, instead of a regular DC power supply, you're going to be working with what's called a function generator. And we're going to be setting it to the square wave mode. And so, if you set the amplitude to 2 volts, for example, for half the time, you're going to have a voltage of 2 volts. And in that situation, the capacitor is going to charge. So the capacitor is going to gain charge. When in the other half of the cycle, the voltage is going to be 0 volts, and what's going to happen is the capacitor is going to discharge. So when you get a positive 2 volts, the charge in the capacitor builds up, and when it goes to 0 volts, the charge in the capacitor goes back down to 0. Now, we can't measure charge directly, but we can measure the current going through the circuit. And current is the derivative of charge, but that means the charge with respect to time. But that means the charge is the integral of current over time. So we can integrate over a charging cycle or a half of the cycle or a discharging half of the cycle. And you should measure the amount of charge that builds up in the capacitor. The catch is there's quite a bit of random noise, so you need to be careful. And then there's, in addition, the current probe that we're using is gets some surges in noise. I'm not sure what caused that. So you kind of have to baby the equipment a little bit to get decent data. But you'll be able to see that in the video clips. And so you connect the circuit. You're going to set the period of the function generator to 3 seconds, and then the data collection time to 1.5 seconds. So you get either a charging event or a discharging event. And so you set the amplitude of the voltage to 2.0 volts. When you get a clean reading, and what you'll see is that not all the readings are clean ones, so you have to be patient. But when you get a clean reading, where you can clearly see either a charging event or a discharging event, and the random noise is not 0, but small enough that you can see what's going on. When you get a clean event, you click the integrate function. And again, you're integrating over time, so that's the amount of charge that builds up. Again, keep in mind, even when there's a small amount of random noise, it's enough that you'll get a decent amount of variability in your measurements of charge. And so what you're going to do is do the measurement 5 times for each voltage reading and then collect the average. And you're going to set up a table. You're going to collect the average charge. You have it in coulombs, but you're going to multiply that number by 1,000,000 or by 10 to the 6 to put it in microcoulombs. And the reason I want you to put it in microcoulombs is that when you calculate the slope, you're going to plot Q versus delta V. You're going to calculate the slope, and the slope will be given in microfarads. And so, make it more easier to compare with the measured readings you got off the DMM. So you're going to go to 2 volts, 4 volts, 6 volts, 8 volts, and 10 volts. And so once you've done that, you plot Q versus V. And again, for each voltage reading, you're going to take 5 measurements of the charge. So you get your slope and you get your uncertainty of the slope, and see how well that compares to the measurement you get from your digital multimeter. So you're going to do that for C1 by itself, for C2 by itself, for both capacitors in series with each other, and for both capacitors in parallel with each other. And so there's one video clip for each of those. So if you have any further questions, go ahead, or you're welcome to email me, and I'll get back to you as quickly as I can. But go look at those videos, and good luck with the experiment.